Good morning, everybody. My name is Helen Cochran. I'll be the moderator for this session. It's my pleasure to introduce the team working on this presentation, which is product quality improvements using performance standards to ensure that a product is safe. We're going to hold all of our questions to the end, so we make sure we get through all of the content. This was a team presentation by Tricia Karg, Dave Brienza, Jack Fried, and John Perlman. Our presenters today are Dave Brienza and Jack Fried. I'm going to hand over now. I believe Dave's going to start. So we'll welcome Dave to the podium.
Thanks, Helen, and thank you everyone for being here, and thank you everyone for tuning in if you're watching this streaming at some time in the future. So before I start, I wanted to just acknowledge that the work we're presenting here today is the work of a lot more people than just Jack or I, or even the people that Helen mentioned. There's a big team behind this work, and I've represented most of them here, but there's a whole other kind of level below this of students doing testing and other people who aren't acknowledged here. So I'll just acknowledge them as well. Jack and I guess, got tapped. I'm not sure why, Jack. I think it's because we're the best looking out of the whole team.
I concur personally. But.
Yeah, I'm sure that's it. So so we're here representing this group, and we're going to talk about how you use standards to improve quality of products and how you use standards to help you select products. So we know that wheel mobility devices, wheelchairs in particular, they fail often. There's numerous studies that show failures are very, very common. The graph I have here on the right side of the screen shows that some 60-something% of devices fail within 2 years. Now, some of these failures aren't serious, but other studies have shown that actually 1 out of 3 of those failures results in some adverse events, like somebody missing school or work, or even an injury. So these are serious consequences. We also know that just using a wheelchair stresses the body of the user. When it's a manual wheelchair, if it's difficult to propel and it's propelled a long way for a long time, upper extremity injuries are common. When there's sustained pressure between the person's buttocks and the seat cushion, pressure injuries are a risk. So there's all these issues that can cause failures or cause health issues. And so our objective was to look at some way where we can judge the performance of the devices to somehow reduce these adverse effects, or at least predict them. So about 5 years ago, we proposed this idea to NIDLR to develop this research program to look at standards and how you can improve the standards and how you can apply the standards. And so we were successful in getting this funding for a rehabilitation engineering research center. And the work you're going to see here is part of the result of that center's effort. So our purpose is, we're just going to go over standards and review them a little bit, let you know what they are, what they aren't, how you generally use them, what the philosophy is, and just so we're all on the same page. Then we're going to get into the meat of it. We're going to explore how data collected from the real world, and Jack's going to talk about this, can predict, or how it correlates to failures we see in the standards world, in the laboratory testing. And then finally, I'm going to talk about how you can take standards that are designed to produce metrics that predict tissue integrity management related metrics to risk of developing pressure injuries, and also how you use that information to compare one product to another. So starting at the beginning now, just the basics on standards. What we're talking about are test methods. So these are methods that are conducted in the laboratory without humans to generate these metrics, which are designed to produce some measure of performance. So these standards are published by national and international groups. So at the international level, we're talking about the International Organization of Standardization, ISO. And in this country, in the United States, in the area of assistive technology, standards are published by the American National Standards Institute, and RESNA is an accredited body by ANSI. So the process of developing standards is interesting and it's important, and unfortunately, it's very long. And so, that's the other thing I should have said at the beginning, is these standards are kind of the product of our community. There are many of you in the audience here participated in these developments, and we're sort of sitting on the shoulders of the community here who have developed these standards. So they start with a market need. So, in the area of wheelchairs and cushions, I've sort of described those needs. There's failures out there. Why are these failures happening? In cushions, we're having pressure injuries too often. What can be done about it? And then comparisons of products from one to another is also a really important aspect of this. And this is particularly important in cushions, which I'll explain later. So they're developed through this multi-stakeholder process. The stakeholders include people like industry, like the manufacturers, clinicians, of course, the users, researchers, policymakers. All these different groups come to the table together to develop these standards to make sure that all those interests are accounted for. They are based on expert opinion and validation results. And so we'll get into that a little later. In the end, a test method goes through a process of gaining consensus where all the stakeholders involved in the development process come together and they vote. They literally vote on the acceptance of these standards, and in that way they're approved by consensus. And all these steps are important, but in the end, these standards are voluntary. I mean, these are methods that are put out there for people to use, but they're not required by ISO, they're not required by ANSI, they're not required by RESNA. They're voluntary methods. They're pieces of information. They can gain teeth, so to speak, when, like, for example, a policymaker would adopt the standard and put some limits on the metrics that come out of these tests for one purpose or another, like whether or not they're going to pay for it or not. So I mentioned the stakeholders, and this slide just tells you sort of how the standards can benefit all the various stakeholders. So let's see better here. So they generate these criteria that manufacturers can use to benchmark their products. So as these products are being developed, they can be iteratively tested with these approved methods, these standard methods, and they can improve the performance of their products in the development process. They can be used to ensure safe, reliable, functional products, because the metrics themselves are designed in the beginning to relate to the important characteristics related to safety or some other aspect of performance, like pressure distribution or something like that. So they can be used to grade performance. They can improve cost effectiveness. They can be used to compare products for people who are selecting products, like clinicians who are involved in choosing one cushion over another. The metrics can be used to compare relevant performance. Terminology is established with the standards. And as I said, sometimes the teeth come when people use the metrics to make purchasing decisions or reimbursement decisions. So a couple things standards aren't and shouldn't be used for. First of all, there aren't always pass-fail criteria. In fact, in the standards we're talking about, there usually aren't. In some cases, like in some safety-related metrics, there are pass-fail, like flammability, for example, would have a pass-fail criteria. But in general, these metrics produce a number on a scale, and what the numbers on that scale mean depend on the actual needs of the person using the device, not the number itself. So how well does it match their needs? And they're by no means meant to replace clinical reasoning. So the output of the standards aren't going to produce an algorithm to choose a cushion, for example, without some additional information being provided by the clinician. They're not for that purpose. So I borrowed this slide from Kara, so sitting here. And so this is kind of the view we have in our standards world of how the information that's generated with the standard gets integrated with the information from research, which gets condensed into clinical practice guidelines, and the knowledge and experience that the clinician brings to the table when they're evaluating an individual. So we see this as sort of this three-area Venn diagram, where all these areas of knowledge come together where a decision is made. So Jack, I'll hand it to you.
Yeah, thanks, Dave. So hi, everyone. I'm Jack Freed. Nice to be presenting in front of you this morning. So I'm going to talk a little bit about caster standards and how we use real world performance to understand that and develop this standard. So some of this, if you were at my talk on Thursday night, might seem a little familiar, but we're going to go through it anyway again for everybody. And also, instead of kind of the outcomes we've developed for best practice and whatnot, this is going to be more about our actual standard. So the caster testing really came about because we were seeing such a disconnect between what we were seeing in the field and what we were seeing in the lab. ISO testing for whole wheelchair testing, so your double drum, your curb drop, all your different tests like that are great for holistic chair testing. But we were finding that through many previously reported studies that there's a high amount of specific component failure, especially casters. About one third of all wheelchair failures are casters, and that's been validated through many different studies analyzing this, and also the data we looked at as well, right around a third there. So, if the whole wheelchair testing was really reflecting what we see out in the field, we would see a large amount of frame failures, for instance, and things like this, but we're seeing a lot of caster failures. So we really understood that we had to understand why those failures were occurring, and kind of start isolating these components to understand how they perform. So we partnered with Labor Tracker to analyze their data set. It is a large data set gathered from technician reported information. So whenever a technician goes to service a failure or anything like that, they record what the failure was, how long it took them to repair it, how long it took, when the failure actually occurred. And we were able to analyze this for many components, but what I really focused on was analyzing the casters. And so real quick, I just want to go over, we were able to categorize these failures into two different larger groups, and then within that, two different failure types. And so I want to go over these, as we're talking this, so you have a bit of a visual. So the first failures we're looking at are your high risk failures. These are your wheel fracture or your stem fracture that you can see in the first two photos there on the left, as well as a bent caster. This is a type of failure that causes immediate danger to the user. So if, for instance, a stem fracture occurs, this causes tipping, this causes the user to fall out of their chair potentially and injure themselves. But it also, on top of, limiting them from everyday life, school and work and all that type of stuff, it also leaves the chair completely unusable. If your stem fractures, you don't have a caster, your wheelchair is not functioning properly. So these are failures we really wanted to understand how frequent they were and understand, how often we're actually seeing and how we can potentially prevent failures like this. Because the other category of failures here are low risk failures. These are something like bearing fracture, which is in the middle right there, and worn out tires, which is all the way on the far right there. And these are failures that do not cause immediate harm to the user. They still allow the wheelchair to function properly. So these are failures that, in some way you would say a bearing is supposed to function like this, right? It takes the load off of the caster and protects it. So when the bearing fails, that means it's really just doing its job. But what we want to avoid is prolonged periods of these low-risk failures occurring and not being addressed. Because once something like a bearing fracture occurs, or something like a worn out tire, then the caster is now much more susceptible to something like a high-risk failure. So even though these aren't immediate dangers to the user, they are something we are still looking to potentially try and prevent and sustain the life of the wheelchair. So as we're going through these, the colors are actually going to be what I use to kind of show some of these distributions for the casters. So I just wanted to go over this so everyone kind of has a visual in their head as we're going through this data. And so the first thing we were able to gather from power wheelchair failures is this is one distribution showing the same manufacturer, but up their different group numbers. So as you can see, the red over here is your wheel fracture. And as that group increases, so as the complexity of the chair increases, you're actually seeing a larger amount of these high-risk failures. And this is a trend we see throughout all of this data as we're going through it, that the more complex seating needs that you have, the more likely you are to experience a high-risk failure. So this was something we found from the data that further supports a lot of other studies that something like caster testing needed to be developed and completed. And then also, this is just showing, this is the same, group 3 power chairs, but across 4 different manufacturers. And you can all see there is not too much of a significant difference here between how those models perform. Very similar distributions of the high-risk failures and the low-risk failures, showing that for the most part, there's a pretty good amount of consistency across manufacturers for their models. And we were also able to plot some survival curves. So this is basically showing the total population of casters from our data set that are surviving. We were able to take purchase dates and failure dates, or maybe repair dates to failure dates, and actually understand how long these casters were surviving out in the community. And just 2 important things to point out. You can see over at the 50% line over here, both manufacturers right around 50% of the casters we had in our database failed right at a year and a quarter. And then none of the casters survived past 2.5 years. And then when we look at manual chairs, we were able to actually compare tilt and space to ultralight wheelchairs. And essentially, this is again showing our major finding from this, that as you increase your complex needs for your seating, you're at more risk for high-risk failure. So you can see the tilt and space wheelchairs actually have right around like 50% failure risk for wheel fracture or bent caster, compared to ultra lightweight wheelchairs that have a much higher amount. You can see like a large amount of bearing failures amongst these. So this is, again, failures that are preventable, failures that also are easily replaceable and repairable to continue function of the caster. And another thing we were able to do that I think is important to mention still here, even though it's not necessarily standards, it's a little bit more about the repair and maintenance, is that a potential cause of this is that ultralight wheelchairs have a much higher amount of service repairs. And so these are repairs logged in Labor Tracker that were not completed due to a failure. They were completed as just like routine maintenance while they were maybe replacing something else or whatever it might have been. So these are not necessarily components that needed to be replaced, but they were just to ensure continued use of the caster. And you can see that the tilt and space chairs had a lot less of these service repairs done, and also had a much higher risk of high-risk failures. So this was something that we have started to gather to kind of start informing some of our repair and maintenance strategies. And so a lot of this data really points to a testing method that does not accurately describe what casters experience every day in the field. And so a big part of that is the durability and the impact of it, and the actual loads it's experiencing every day. But also a big part of it is the environments in which they're operated in. And so in less resource environments, or any environments like rural areas in America, or rocky terrain in Scotland, dirt roads, high humidity, all of these things really, really affect the caster and its lifespan due to things like corrosion, dirt, debris, and then, of course, you know, if you're experiencing uneven terrain, that's a lot of impact and shock being dealt to the caster. And so after really consulting a very large group from the ISWP standards working group with this, and researchers here at the University of Pittsburgh, we were able to develop a addition to the ISO standard testing, ISO717632, that is able to test these casters. It's been validated, it's been incorporated last year, and it's able to simulate not just the durability testing and the impact that casters face, but also the environmental conditions that they're exposed to. And so I'll get a little bit into the test method here as we move on to start talking about how it's applied. The first step of the process is actually simulating corrosion. And so we put these casters into what's called a salt fog chamber that basically heats up and disperses salt fog into the chamber, and actually exposes them to things like corrosion. So they sit in this chamber for 200 total hours. Half of that time they're being exposed to the actual salt fog, and the other half of the time they're sitting in there and allowing the corrosion to actually develop on the caster. So we have them start that, and then once they have finished that 200-hour period, we move them on to the here we go. We move them on to the caster durability test. So this was developed by many people, Anand Matre, John Perlman up here, Joe Ott also contributed to putting this together. And it is a turntable device, which not pictured here, but we also lay out sandpaper, coarse sandpaper onto it to expose it to things that simulate like tire wear and things like this. But then also we have metal slats on this. And I think, yeah, we have a video for it, so you can actually see it in action. So depending on the size of the caster, it will be exposed to different loads and different configurations and cycles to accurately test it. And so you can see we also have it move in the reverse direction. We reverse directions many times every 100 cycles throughout the process. And so combining it with the corrosion and also the durability testing is what allows us to get a much more accurate idea of how casters really perform out in the real world. So what are we using this standard for? Oh, there we go. So when we're trying to raise the device performance using this standard, we can use it in many different ways. And it can really be used to inform design. So what material choices are you making on your caster? What lengths and actual, dimensions of this material you're using? What is the actual design of your caster? We can also check the quality of currently existing casters. So design might be something, where we explore new ideas for caster development and test, how they perform compared to other casters. But quality is testing, okay, what casters, are already out in the field. So we've been able to partner with many different groups that supply casters and also manufacture casters to start providing them accurate reports on how long they can expect their casters to actually perform in the field. The standard has a 2-year equivalent of cycles requirement on the test, the durability test. So we're at least trying to hold these casters to some standard of usability for a certain amount of time. It can also really help to inform selection of casters. So understanding, based on the environment someone's in, based on their use case, how active they are, we can make decisions using these standards to actually help inform what casters they should use. And this can also be used to show the effects of maintenance. I know, one study we really want to do is actually demonstrate a form of preventative maintenance on this test and actually replace components while it's on this and see if that extends the life of casters that we were very aware of how long they last on the machine. But a few studies I want to just go through to show how we've kind of applied this is actually a design study. So I looked into if you were to replace something like a metallic ball bearing, which is very susceptible to things like corrosion, dirt, debris. If you replace it with something designed to resist these things, so something like a thermoplastic bushing that is not exposed to corrosion, is not affected by corrosion as much, and also is a solid piece, so it's less susceptible to having like dirt and debris invade the bearing. We really wanted to see if that would actually raise the performance of casters. So what we did is we chose two different thermoplastic bushing materials, and we compared them to the standard ball bearing that came with these casters. We chose one caster to isolate the performance of the rolling element. So we wanted to compare them to that standard bearing it comes to, but then also we wanted to compare it to a much more higher end, higher cost bearing to see, is that a better application? How does it compare to those? And you can see we really wanted to focus on understanding its actual durability, but also its cost effectiveness. So that's why we also have the prices here of each bearing. So as you can see, the chrome steel bearing over there has a much higher cost to it. And we wanted to see if that would factor in compared to the much more similar lower priced rolling elements. And so we had them test into the salt fog. We had them sit in there for 200 hours, and then we tested them to failure on the caster durability. And here are some of the failure distributions here. As you can see, the standard bearing all experienced, sorry, I got to make sure I say this right, the bearing fracture. And then each of the other samples had two samples. We tested 4 samples, 2 of them for each other one passed, that's the green. But then, 2 of them also, all 3 of them had at least one stem fracture, and the double seal bearing also had a bent wheel or fork when it was going through the testing. And you can see pictures from those failures depicted up there. But really, the biggest thing, even though it was still experiencing these failures, the biggest thing that came out of this was the amount of durability these bushings actually provided, and the cost effectiveness that these bushings provided as well. So as you can see, both the thermoplastic bushings had pretty high durability. You can see the second one we tested actually had the highest amount of durability. That's the bar part of the graph. I know there's a lot going on. The gray line in the middle is the 2-year standard that we compare them to. As you can see, the standard bearing actually fails right at that 2-year period, actually a little less, right about a year, 1.8 years. So that had much lower performance. But then, the bushings and the double steel bearing had very high amounts of durability, far past the amount that we actually required for the study. We tested them to at least 6 years, I would say. And because the reasoning for that is, well, the whole chair is probably getting replaced at that time. So we didn't feel like we had to test much longer, because at that point, you're probably replacing your whole device. But the big thing that came out of this was, you can see the orange is actually the cost effectiveness. Both of the bushing samples had extremely high cost effectiveness. So it's basically the amount of time it lasted per dollar. And then you can see, even though the double sealed bearing had really high comparable durability performance, it's so highly priced that the cost effectiveness is the lowest out of any of them. And so this was one study we wanted to do to really show, can design changes with materials be done to actually raise the overall performance of these casters? And we were able to show that using this standard. Another one we did actually was we did not really test any tilt and space caster models when we were validating this caster test model. And so when we analyzed this data and found how much higher risk that these tilt and space models were to dangerous failures, we wanted to try and test this and actually simulate these failures. And so we chose two different tilt and space caster models, a 6-inch and an 8-inch. And we wanted to see how they would perform compared to the time to failure that we were able to gather from the data set. So we had an average time to failure that we were able to gather from the community data, and we could compare that to its performance on the caster durability. So again, we had these casters run through this testing and produced these failures. I will say actually each model failed the exact same way, which is one interesting finding. So for the 6-inch, they all failed with worn out tires until they were unable to be used. And then the 8-inch all experienced a crack right there at one of the spokes of its stem of its wheel. So the other thing that the big finding really that we wanted to do here is actually see the breakdown of these caster models from the community and compare it to the lab simulations. So for the 6-inch, the worn out tire, you can see compared to the lab, we see that worn out tire only represents 21% of what we're seeing in the community. When the lab, it did represent every failure we saw. The same thing with the 8-inch model, we were seeing cracked wheel. And luckily that was the most reported failure in the community as well. So those technically did match. But you also see that in the community, there's a lot bigger of a spread across these failure modes. And then the 6-inch also had a really, really big difference in its time to failure. So in the community, it was right at 2 years. In the lab, we actually saw it last as long as 5 years. And then there was a slight difference for the 8-inch as well, 2.88 years compared to 1.57. And so what does this tell us? I think really what it's saying is that we need to understand tilt and space casters more. And maybe this is another instance where we need to develop more specific standards to actually understand how tilt and space casters perform in, compared to ultralight. Because really there is a very different use case between the users who use ultralight wheelchairs and users who use tilt and space. And so really what this finds is kind of further research to continue to understand how these casters are performing. So that's just a little summary of some of the studies we've been using to do this, on top of also just providing reports to manufacturers and other organizations who supply casters on how their casters perform. So we can move back over to cushions.
Thanks, Jack.
Oh, yeah.
So in the area of cushions, the clinical goals of cushions, I might sort of think of them as three. One is comfort, one is providing a stable base, and also to protect against pressure injuries. And if you think about those three goals, sometimes they're conflicting, sometimes they're coupled together. Sometimes there are unique needs of the particular person that would point you towards one solution or another. But in the end, out there on the market, there are more than 200 cushions, marketed for use in wheelchairs, probably much more than that. And how do you choose? I mean, it's impossible for anybody to really be familiar with 200 different models of cushions. It's too many. So the basic question that we were thinking about when we started this work was, can we help people select cushions, and can we use the standards to help in that selection process? So we knew we had these test methods, these standard test methods, and they've been developed over a course of 20 or 25 years, and some of them are very mature and some of them are a little bit newer, but they all are designed with producing these metrics. which grade the cushions along these various levels of performance related to at least stability and the protection of injury. Comfort, maybe not so much. And so these methods are sort of grouped here in the area of pressure distribution, stability, microclimate control, which is the regulation of moisture, humidity, and temperature. And then there are tests that are sort of safety oriented, flammability, and then finally there are durability methods. And so I'm going to focus right now on just immersion, envelopment, and stability. And immersion and envelopment are the characteristics that we use to grade pressure distribution. So all of these methods use analogs of the human body, and they're rigid indenters. And I have a couple up here, and there's 3 different ones here, and they're used in different tests, but they all represent different portions of the pelvis, essentially, or the interface between the human body and the cushion. And so like this indenter is designed to represent the ischial tuberosities and the greater trochanters as the rigid structures, and then some continuity between those structures. This one is the one we use for envelopment. It represents just a little bit more of the pelvis. It's sort of got another dimension to it, in the posterior, anterior direction, and it's a little bit more of the pelvis. And then this is the one that's used more commonly. This is just representing the whole seated interface, and it's made out of wood. It's hard indenter. We use rigid indenters in these tests because what we've found over the course of development of these methods is that in order to get the reliability and the repeatability in the results in those metrics, we needed that rigid interface. And so in our center, we've tested more than 50 different cushions with all the different tests and generated piles and piles of data. And we're like, great, we have all this data. We know everything there is about these 50 cushions, which we chose to represent, the market of these 200, and they do a pretty good job of representing the market. So let's unleash these on the public and let you use the data. And so we went out and we said, well, how, here's the data, clinicians, can you use this? And they're like, no. We have no idea what to do with this data. You tell me what it means, and we'll go from there. And so that put us in a bit of a quandary because our philosophy is, well, we don't know what people need. We just know what cushions do with these test results. And so just knowing what the cushion does doesn't solve the problem, and just knowing what the person needs doesn't solve the problem either. There needs to be some coming together of this sort of clinical application of the data. And so that's the problem that we're working on now, is how do we take this data that we produce that we believe corresponds to the performance of the cushions and get it applied so that people get cushions that they need and solve their individual problems. So the approach we're taking now is we've taken all our data and we've made it accessible on the web. And you can, if you don't want to listen to me anymore, you can actually do this right now, but maybe wait till later. We put all the data out there, blinded. So there's that. In a visualization scheme that we've sort of developed, in consultation with people who are potential users of the data, sort of bar charts and ranges. And we have this interactive tool. Go ahead, Jack. And so if you go to the website, what you're going to see are these icons representing the different areas of performance that I mentioned before. And if you click on one of the icons, and I think we're going to go to immersion here, you'll see an explanation of the test, sort of what actually is this test. And this is the test that's being described here is the loaded contour depth test, and it uses this this crude looking indenter here, this metal cylinders with a strap between them, and describes how when you press this down into the cushion, you measure how far it sinks down into the cushion, and that's the metric, is how that depth of immersion, how far it sinks down. So if you think about now the marketing and the manufacturing side of this, I mean, the challenge that the manufacturers have is they've developed cushions with specific sort of uses in mind. This is a cushion that's going to help people, be stable in their wheelchair. This is a cushion that's going to protect them against pressure injuries, or this is a cushion that's going to keep them cool. Whatever it is, the engineers in these companies have developed features of these cushions that affect these outcomes, and they market it. They put on the website, hey, this cushion has good pressure distribution. Okay, so I mean, probably what comes into your mind when someone says that is, oh, when I sit a person on this and with a pressure mat, I'm going to see blue and green and not red, right? And that's good pressure distribution. Well, unfortunately, we don't have a standard that uses a pressure mapping system for that purpose. We do have one, but that's another story. The tests we have are the immersion and the envelopment tests. So if your interest is perhaps you want to prioritize pressure injury prevention, you're very concerned with pressure distribution. So it's the immersion and envelopment tests that you're going to want to look at. So I'm going to talk a little bit about those two tests and the results we saw with our cohort of 50 cushions. So I already described the test. I think we can skip to the next slide. So here's how we visualize the results, or currently. We are definitely open to suggestions on this, because for you practitioners in the room, we really want to know what is useful for you. This so far, this is what we've come up with. So each bar in this chart represents the immersion depth from this loaded contour depth test for a particular cushion when we did the test. And the black bar, K here, I don't know, you can't see the letter, but this black bar is a reference cushion. That is just a 3-inch thick HR45 foam cushion without a cover, with a cover. And so you can kind of get an idea of how cushions perform relative to that standard. You can see for that result. One thing that I like about this right away is there's a big range here. So what that tells me is that for all these cushions out on the market, which are representing the market, they actually perform quite differently on this test. So there is a difference here. So that tells me that this is a valuable test, because it's differentiating performance for the cushions in the market. And there's go back, sorry. There's cushions, on the high end, there's some on the low end, and there's kind of this, looks pretty linear between the two. Yeah. Yeah, good question. So we can, even on our website, we have a way you can say, how do the skin protection cushions, like by code? I'm going to talk about by code first. So by reimbursement code, you can sort them by that, and you'll come up with a different color for each code. We did do exactly what you asked, is we said, okay, by material and construction, how do they perform? We didn't put that on the website, and we didn't for a philosophical reason that we feel pretty strongly about, and that's, we don't think that materials and construction should be used as a criteria or as a surrogate for performance, because all air cushions don't perform the same, all foam cushions don't perform the same, and you'll see, if we did that, there'll be some air cushions up here, there'll be some air cushions down here, there'll be some foam cushions up here, and it's really not it's not productive to do that, actually. Next slide. So I talked earlier about standards getting teeth. This test has teeth because this test was adopted by Medicare to decide which cushions get coded for skin protection reimbursement category, the skin protection reimbursement category. And they took the test and they didn't put a threshold on the actual linear measurement, the depth. What they did is they said, okay, you load this with the prescribed load and you see whether this trochanter button touches or not. If it touches, it passes. It will, in the case of skin protection, 40 millimeters, it will be given that code as long as it satisfies a couple of criteria. If it doesn't touch, it fails. And so there's two different size indenters. There's a 40 millimeter indenter, meaning there's a 40 millimeters between the bottom of the ischial tuberosity cylinder and the trochanter cylinder. And then there's a 25 millimeter model where that distance here is 25 millimeters. And the 40 millimeters designates skin protection. The 25 millimeters designates general use. If it's below 25, it doesn't get coded at all. So that test seems a little crude, right? I mean, this thing is ugly. No offense, Steven Sprague isn't here, but he developed this. It seems crude and it almost seems too simple. So there was some sort of thought in our standards group that, we need sort of a more sophisticated measurement of how pressure is going to be distributed on cushions. And after many, many years of thinking about this and trying to develop this, the result was this envelopment indenter that I have. This is a dummy of it here because these sensors are way too expensive to play with. The result was this envelopment indenter, and it includes 18 very accurate pressure sensors embedded now into the indenter, so that when you push this thing down into a cushion, you can measure how much force is being put onto each of these sensors, each of these pressure sensors. The idea is that for a highly enveloping cushion, so sort of the most, I guess my most general definition of envelopment is how even the pressure distribution is, or how low the pressure gradients are. It actually technically means how well does the cushion conform to the indenter or the person. So in this test, what we look for is not so much a number coming out of this, but sort of a shape of this curve, which is the profile of the pressures along this medial lateral line of sensors. And so when we see that profile is relatively flat, we judge that to be more enveloping than one that's sort of peaky, which would represent more force being supported on the apexes of these spheres. There is time involved, but it's about, I think it's in this test, it's only 60 seconds, I believe. Well, don't quote me on that. It's either 60 seconds or it's 300 seconds. Some of the tests are a little different, but that's the only time. So how does this relate to like marketing? I mean, you will see manufacturers talk about envelopment because we all sort of agree that this is an important characteristic. And so generally the way we see this being marketed is they talk about sort of optimal distribution of pressure. And the way we interpret the marketing sort of jargon of optimal distribution of pressure is good envelopment. So that would be, if you want to sort of check if the cushion you're considering has an optimal distribution of pressure, you would look to the results of this envelopment test. And you can see kind of some interesting things here, like for example, offloading cushions. One of the impetuses of developing this was to have some metric that could represent what an offloading cushion would do relative to a cushion that was sort of designed for more continuous contact or continuous support. And on this indenter, when you load it against an offloading cushion, you can actually see areas which bear very little or no support or pressure. And so in this picture you can see like these sensors, like 1, this 3, 6, or 1, 2, 6, 6, and 8. They're sort of dropping out, meaning there's a relief there in the cushion. So you can see it with this test. So moving away from pressure distribution, that one of the other goals of a cushion is stability, providing that base of support. And so this is a newer area of the standard, and it was developed over the last 5 or 6 years or so to look at some metric that would be indicative of how well a cushion provided this stability. So there's actually 2 tests. Just go back one quickly. So that's what the lateral stability test. There's actually an older test called impact damping, and that's a test. It actually is just what it sounds like. It's a test of impact damping, which we also consider to be a measure of stability. So the lateral stability test is a test where you load this indenter, and you can see this is interesting. The indenter has genes, and that was for this test, actually, why we did that, so it wouldn't slip out when we shifted the center of gravity. Because what this test does is we put this straight down on with the load centered, and then we shift the center of gravity of the load, and what happens is the indenter tilts. How far it tilts is the metric that we get from this test. The more tilt we get, we judge that to be less stability, because it's indicative of the cushion's reduced ability to resist that lateral tilting. So going to our results from our 50 cushions, again, we see like a big range here. That's good. It's a good test in that it's differentiating products. Interesting here, like here's our reference cushion. Here, so you're showing the reference cushion is showing a lot of tilt, so less stability. The other things I see here is, there's kind of this big group in the middle that are relatively the same. This is the range is 0 to 7, 8 degrees. And then there's some highly stable ones here that resist tilting. And then there's these over here that sort of let this thing go and tilt. They wouldn't be probably very stable at all. The other test related to stability is impact damping. And so this test, it measures how well impact loads are absorbed by the cushion. And so a cushion that doesn't absorb impacts very well is going to have this sort of bouncing effect. And so if you picture someone riding off a curb in a cushion that didn't absorb impacts very well, you might hit the bottom of the curb and then you'd sort of bounce and slowly settle, right? But other cushions may absorb that impact and then not sort of result in that bouncing motion. So that would be more stable than the one that sort of made you bounce along until that died out. So if you could just run that video. So this is a video of the test. We set up the cushion on an angle with a load on it, and then we pull the block out, and we see how that we see what the acceleration of the load, what happens to the acceleration of the load. And so this plot down here on the right is sort of a one that doesn't have very much dampening, so it kind of rings, it bounces. This result, I don't think is that. So don't try to connect the two together. That's just representative. The metric for this test is the ratio of the second impact, the magnitude of the second impact to the magnitude of the first impact. And if you probably can't see the scale here, but we're talking about accelerations sort of in the area of 20 meters per second squared. If you saw Dr. Sprigel's presentation yesterday on vibration, he's talking about vibrations, I don't know, in the low single digits. This is accelerations in the low single digits. This is an order of magnitude or higher than that. So when we look at the results from our 50 cushions, again, great. We see a big range here. We see differentiation between cushions. You see our reference here now is showing relatively poor damping. So this a low number here represents more ringing because the ratio is closer. And if you were looking at manufacturer's information, if they're saying, okay, well, this cushion provides stability for the user, you might look to these two tests just to sort of check them on that and see. And if your client prioritize stability, you might go to your data and say, look, where do I fall? Can I do better? Is there something that's going to give me better stability? Or yeah. So like I said, all this data is online right now. You can go look at it. Unfortunately, we do have the actual cushion models blinded, and that's right now due to some agreements we had with the manufacturers that provided the cushions. But we're hopeful that some manufacturers will permit us to unblind the data, and some manufacturers will hopefully start to make this data available on their own sites, and some are, as a matter of fact. And so you can start to see that, and that's sort of our goal, is to see this widely available. But you can always request it. Almost all the manufacturers do this testing, so they know how their cushions are performing along these metrics. So you can request the information, and then you can just go and see where it falls in our cohort to know where it falls in the sort of the world of cushion performance. But there's also fact sheets there, explain the tests, and a bunch of other resources related to wheelchair and cushion standards. Hopefully it'll help you. And as I said, we're always open to feedback, so we can improve the way this information is translated. Yes. Well, yeah. So the question had to was that in the long-term care, would we provide education to the long-term care facility community? Yeah, we definitely would, including our home UPMC. We see that as part of our mission, so we'd be amenable to that. Yeah.
Yeah.
Just repeat the question for the recording.
Oh yeah. So the question was, just kind of stating the casters that we use for Tilton Space and how those are, slightly more upgraded versions of those casters, and we should probably look to use something that's more like by a 1-inch for those the 8x1, the 6x1. I totally agree, and we need to test more and more of these. We were kind of led to test these because this is what we had the real world data to, we had a lot of failure modes, but we didn't always have the ability to actually calculate how long they were in the field. So after breaking down all this data and really seeing what we had to use, these were the two we had the best data for, which is why we did choose those. But I absolutely agree. There's more standard casters to choose. So.
Do we have time for one more? Yeah, absolutely. We've looked at ways that we can combine the results from multiple tests to sort of start to group the performance along multiple dimensions instead of just one. And we think that would be really useful. We're trying to figure out how to do that. You know, some of the analytical methods we tried so far have not been successful in grouping those 50 cushions. But the other piece of that is what you mentioned, is sort of the profile of the person. Is there a person, sort of a profile of a person that would match to a group of cushions, which matches to a group of performance? Yeah, we think that would be useful, and we think there's some potential that will happen.
So we're just a little bit over time. So I'm going to thank Dave and Jack for speaking with us today. We can still answer a few more questions, but for those of you who would like to get to the next section, I will give you the CEU code.